Hello, my name's Hassan and welcome to my rational function project video for AP Calculus. I'm going to be analyzing the function r of x here, and to the left it's its graph, so now let's get into it. Firstly, I want to establish that the numerator, which we'll call f of x, is equal to x cubed minus x squared minus 4x plus 4. And this is a polynomial since its powers are raised to non-negative integer and its coefficients are real numbers. And the same applies to g of x. The same rule applies to g of x, making it a polynomial function. Now, when we expand it, f of x, we get x minus 1 in parentheses, x plus 2 parentheses, and x minus 2 in parentheses, giving us the rational roots of x is equal to 1, negative 2, and positive 2. Same for g of x. When we expand it, we can see x is equal to 2, which will get canceled out later in a sec. X is equal to 0, and x is equal to minus 3. After cancellation, we see, as I mentioned, since both the numerator and denominator share this negative x minus 2, we can cancel it out, and we see that it has the real zeros of x is equal to 1 and minus 2. So r of x, the entire function, has roots at those points, since that's where the entire function will be equal to 0. And we look at the zeros purely in the denominator, which is 0 and negative 3 after cancellation. Those produce vertical asymptotes, since when x is equal to 0 there can't be any value, since the function will not exist, since we can't divide by 0. The horizontal asymptote, since the degree of the leading coefficients are both the same, we take the leading coefficient, or the degree is the same, we take the leading coefficient numerator and leading coefficient denominator, which is 1 and both. So 1 over 1 is equal to 1. So the line of the horizontal asymptote is 1 equals minus 1. And then, as we established, since we canceled the factor x minus 2, we get a whole at x is equal to 2. Now, the name of my function is called limit lock, and I'll explain that in a sec. Okay, so as we see, as x tends towards infinity, r of x approaches 1. And then, when we see x approaches minus infinity, r of x approaches 1. So, we see that the limit is locked as we approach infinity from the positive and negative end. And we also see that it's interesting that among our asymptotes, there is no limits. That's because, however, we do have one-sided limits. But I want to get into the whole that we established real quick. Since we had a whole at x equals minus 2, we could simply plug that point in onto the canceled function, and we're going to get 0.4 at that point. But remember, on the actual function, that there doesn't exist that point. That's just where the limit is. And then when we look at to the left of 0, we can see that there's a limit of infinity, and to the right of negative infinity. And for negative 3, to the left there's positive infinity, and to the right is negative infinity, because that's where it approaches. Now, we're going to take the derivative. So, to make it easier on ourselves, we're just going to rewrite it into this standard form. And then we can solve it by using quotient rule. So this is how it looks. And then when we're going to leave it in this form instead of fully simplifying it, because it's going to make it easier to find the second derivative. So then I can't fit all the work on one page, but this is the fully simplified form. Now, if we had factored this when we took because we have to take quotient rule again, it would have made it a lot harder since we'd have to use more rules. So this makes it the easiest. And then we've simplified it. Now, let's take a look at this. The roots, or the x-intercepts, is x is equal to 1 and x is equal to minus 2. As remember, we gotta cancel out the negative 2, and we just look at the numerator for that. And then there is no y-intercept, since from the denominator, we have an x equals 0, so that no point actually touches the y-intercept. Taking the critical points, we need to look at the first derivative and see where it's either equal to 0 or is not defined. So we're going to see at the numerator, when we equate it to 0, we're going to get no real solution since the discriminant is negative. And for the denominator, we're going to see that we get x is equal to 0, and x equals minus 3 where the function does not exist. When we plug that into the number line and plug in points between these, we see that it's the function is constantly increasing on this interval. And this is how you would write it, with a union in between. Now moving on, we're going to be looking at concavity. So we see the numerator is equal to 0 and we're going to do the same thing, find the critical point. So numerator is equal to 0 at approximately negative 1.327. You got to use a graphing calculator. So on Desmos, when you plug this in, the numerator in here and that of the second derivative, and see where its x-intercept is, that's the point you get. And then for the denominator, it's pretty obvious, 0 and negative 3. So those are the critical points. And then when we plug all of these and see the values in between, we see that it's in concave up, negative infinity 0, union negative 1.327 comma 0, and concave down on this point, on this interval. And then these points would probably be, most likely be points of inflections. All right, now looking at this, we're going to go in the problem using mean value theorem. So it says on the interval 3 comma 5, so only looking from 3 to 5, is there a value such that R prime of C is equal R of 5 minus R of 3 over 5 minus 3? If so, find R of C. We can solve this using mean value theorem. So we're going to take a look, and I want to remind us that we did have a hole on negative 2, and we do have vertical asymptotes, but those aren't in. So the function is continuous, and on this interval, it is differentiable by looking at the graph. So there is a point C that would solve it. But we're not trying to find the point C, we're just trying to find the value of the R prime. So to do this, we're going to plug in 3 and 5 to solve for this. And then we're going to get 0.55, 0.7. And then when we plug it in, we see that's 0.0722. And I just want to show you when you plug in derivative, you're going to get the same exact thing, which is this green function is the graph of the derivative. And then this line points where it's at. It's about 0.07. This top part right here is 0.1. Keep note of that. And then just here, I drew a sketch of how the tangent line would look. Intermediate value theorem states if f is continuous on a comma b brackets, so open interval, and k is any number between f of a and f of b inclusive, then there is at least one number c on the interval such that f of c is equal to k. So what does this mean? It's saying that, for example, if we took the point from 1 to 5 and it is continuous, which in this case it's not because remember we have a hole at 2, that there is a value c in between those. So let's use this point here, negative 9 and 5. We know that's completely continuous, and negative 9 is equal to about 1.2, and negative 5 is equal to about 1.8. Then a value in between those then we have to have a value f of c that's going to be in between those two values. Or there's at least one number c, k, which is k, that's between the two values. F of c, which is equal to k, that's between those values. Now, extreme value theorem states if f is continuous on a comma b, then f attains its maximum value, f of c, and a minimum value, f of d, at some numbers c and d in a comma b brackets. All this is saying that if it is a continuous, then we need to have a maximum. If a function is continuous, we need to have a maximum and minimum value at some points within the domain. And let's just use this example over here. If we're going to use 3, the domain as 3, comma 5. We see that's continuous, so there has to be a maximum and minimum. The maximum will be f of 3. The minimum, would be f of 3, and the maximum would be f of 5. No, it doesn't have to be the two endpoints. It could be somewhere in the middle as well. That's just how it ended up in this example. Now we're going to find an equation of the tangent line when x is equal to negative 5. So to do this, we want to use our derivative. Take the derivative, which we have already found, and we want to know the actual value when it's equal to negative 5, which will come in play when we write the equation. So then when we plug in negative 5, we see the derivative at that point, the instantaneous rate of change, is 0.36. And now we write the equation, since it's going to be at that point. This is why we found. So we're going to plug in the numbers, and we're going to plug in negative 5, since it's at that x value. So it becomes plus 5, since x minus the value here. So x minus negative 5, which is positive. And now if we want to find the normal line, what we do, since the normal line is perpendicular, we simply take a negative reciprocal. So after doing that, we see it's approximately negative 2.78, and we simply put that in, and it's going to be the same y and x values here. And that is all for the video. Thank you for listening. Have a good night or day.